Hello, everyone. This is the Steel 3 lecture. I wanted to start this by looking at this project because when we spoke about steel in the Steel 1 lecture, I said that steel historically has always been used tectonically rather than stereotomically. And this may be about to change. And so this is an example of a pedestrian bridge, an experimental project that was constructed in the Netherlands last year and the project is called MX3D. And you can see that in plan it is curvilinear and irregular, and in elevation and section also very curvilinear and irregular. So the photograph at the top is taken in the workshop where the bridge has been made. And you can see that it is basically a solid steel structure. So here again, you see it in the workshop, and it is a solid piece of steel. And the method of fabrication here is 3D printing. So this is robotically constructed. And rather surprisingly, the layers that are being printed in vertical slices rather than horizontal slices. So this is perhaps an indication of steel in the future being used stereotomically. Okay, so in the last lecture, we looked at three steel buildings with steel structures, with steel trussed structures: the Pompidou Center in Paris, the Sainsbury's Center in England, and the Waterloo International Terminal, also in the UK, in London. So today I want to look at a fourth building, the Sendai Mediatek in Japan, by Toyo Ito, and the structural engineer was Sasaki. So this building was completed in 2001. The program for the building is a MediaTek, and this at the time was a new type of building program, again, a hybrid program, which has become a very familiar building typology now. So instead of the bibliothèque, which is the French word for library, this is a médiathèque, which means that it includes all forms of written and audiovisual media. Because of the hybrid nature of this program, Toyo Ito wanted to make a non-hierarchical building which has an unfamiliar spatial order, and he calls this subtle structure. It combines geometric and non-geometric modes of thinking, and his ambition here is to create a non-hierarchical public space, a non-hierarchical cultural center that is more accessible to people both psychologically and culturally. It's important to understand this approach in the context of Japan, which historically has had a very strong hierarchical culture. Toyo Ito won this project in an open design competition held in 1995. The competition was to provide a new civic building for a provincial city about 200 miles north of Tokyo. So the MediaTek houses a library, audiovisual collections, public media workshops, and exhibition galleries. With 6 floors above ground and 2 basements, you can see that the volume of the building is a deceptively simple looking box. It's 150 feet square. So it's a very simple orthogonal volume overall. But and you can see here then the idea of having a non-hierarchical spatial order. You begin to see that what looks like a simple box is actually anything but. There are lots of variables here. So this project began with this very simple conceptual sketch, which Toyo Ito explained as the concept of seaweed dancing in water. And so the seaweed, of course, brings in the idea of some kind of biological metaphor or metaphor from nature. And dancing in water indicates to us that he wants the building to be dynamic, to look as if it is going to move or change, or as if it might move or change at any moment. So the building then is reduced to three basic elements, which Toyo Ito then renames from the typical nomenclature that we use as architects. So instead of columns, he calls the vertical structure tubes, and indeed they are tubes. Instead of floor slabs or floors, he calls the horizontal planes plates. And then he has the skin, which encloses the building. So we have tubes, plates, and skins. And so if you think about Le Corbusier's Maison Domino, in which was a concrete structure, but there he posited the idea of a very regular concrete structure and a non-load-bearing curtain wall, typically a glass curtain wall. Toyo Ito proposes that this building, the Sendai Mediatek, is a 21st century version or update of the Maison Domino. It is, after all, an orthogonal volume, but instead of the static order of the Maison Domino, the ordering systems of this building are dynamic. The structure of Sendai Mediatek is to appear fluid and visually unstable, appearing likely to change at any moment. So on the Maison Domino to the left, we have a very regular frame and very regular floor slabs. And it's only the facade that is free from this order. In the Sendai Mediatek on the right, we have free or dynamic columns and tubes, vertical tubes and floor plates. And then the skin of the building is actually the orthogonal volume. It's a curtain wall, but it is just the orthogonal box. And so the kind of ordering systems here flip about what the structure is doing and what the envelope is doing. The idea of fluidity or dynamism is most evident in the vertical structure of the building. And so there are 13 structural tubes. Each one is differently shaped. They are irregularly placed, and they expand and contract as they ascend up through the building. They shift from floor to floor. And so if we look at this structural model, we can see that at the corner of the at the corners of the buildings, there are 4 large tubes, one at each corner, and these are triangulated. So the steel members are triangulated for these tubes. So these are the tubes that are providing the lateral stability for the building. And yet they appear to be rather fluid and unstable, and they are visually permeable. but they are quite strong. The 9 remaining tubes then are much smaller in diameter, and these are carrying only vertical loads. They also, as you can see, are comprised of only verticals and horizontals. They are not triangulated. So if we look at these tubes, we might say, what are the rules here that are governing the formation of this structure? It's designed to look rather random, but it is in fact controlled by a couple of very simple geometric rules. For all of the tubes, or for each tube, they are circular at all floors. But the diameter of the circle changes from floor to floor, and the center of the circle moves from floor to floor. So it's a geometric rule, but one that allows the structure to vary from floor to floor. So in the photograph on the left, you can see you can see two of the tubes that only have verticals and horizontals. So these are Vierendeel tubes. They don't have any triangulation or diagonal bracing. And you can see that because the center of the circle moves from floor to floor, the tubes appear to be tilted or canted on each floor. And then also the circle can change in diameter. So the tubes can get larger or smaller as they move from floor to floor. On the right, we are inside one of the larger tubes at each of the corners of the building, and this is one of the triangulated tubes which is providing lateral stability. So in addition to the tubes being the vertical structure of the building, they also are the servant spaces and the servicing spaces of the building. And all of these vertical tubes are fully welded assemblies of circular hollow steel tubes. So every tube is made up of a welded assembly of steel tubes. The wall thickness of these tubes varies internally. Externally, all the tubes look much the same diameter, but where the structural stresses are greater, the wall thickness thickens internally in the tube to make it stronger and stiffer. And so you can see in this image, when we talk about servant spaces, that means that we place the egress stairs inside of the tubes. The elevator is in a tube. The vertical ducts are the vertical chases for supply and return air, etc., etc. At the intersection of the tube with each plate, floor plate, there is a void. And so when we look up the tubes, we can see all the way up through the roof, and there's a skylight at the top of each tube. So this is the opposite of what we expect to happen with structure. We expect the column to be solid and not visually permeable. We expect the column to floor slab joint to be solid and very sturdy and not a void. So he's challenging all of these structural conventions with this building. And this image then shows the idea of the vertical tubes housing the servant spaces of the building and the servicing spaces of the building. So the mechanical plant rooms are in the basement, and we have supply ducts. The blue are supply ducts that are inside the tubes, and then the tube itself is the return duct. So we have a duct within a duct. And then we have the egress stairs inside the larger corner tubes. All of the tubes project up 1 story above the roof, and at the top carry a grid of solar shading that sort of hides or conceals mechanical plant on the roof. So the tubes are playing an active role structurally. They're playing an active role in passive servicing, that is, getting daylight down through all of the floors, and in mechanical servicing and in vertical circulation. So they're doing many jobs for this building. The structural tubes are constructed of, as I said before, hollow circular steel sections. And this is fire-resistant steel, which is an alloy that is only made in Japan. It's rather expensive, and so it hasn't found a market outside of Japan. And so that means that most of the steel doesn't need to be the steel does not need to be fire protected. So the steel that we're seeing inside the building is the steel structure itself. It doesn't need to have intumescent paint, doesn't need to be filled with water, doesn't need to be encased in concrete or spray-on fireproofing, none of that, because the alloy here that's used here, the steel that's used here, is itself fire resistant. On many floors, then, there are fire-rated glass enclosures around the outside of the steel tubes. And this is because the voids that connect all of the floors from the bottom to the top of the building have to be separated from the floors themselves. Otherwise, smoke would travel everywhere. But the enclosure is glazing, and so it is almost invisible. So in this section, then, you can see the different tubes. You can see how they undulate from floor to floor. Clearly, the tube that has the elevator in it, the second from the left, has to be careful in its undulations so that it provides the vertical elevator shaft at the middle. And then you can see how the tubes pop up above the roof. You see that better in this 3D model. The tubes pop up above the roof slab and project another story up in height, and then carry this kind of shading grid, which also serves as a cornice for the building. So in addition to the tubes not being set out on a regular grid, not being the same floor to floor, you can see that the floor plates are also floating or variable. So there's no standard floor to floor height. All the floors are different heights ranging from 12 to 22 feet, and they are randomly spaced. So this makes the job of designing the egress stairs slightly more complicated, but the egress stairs get longer or shorter on each floor, depending upon the floor height. He wants to call the floors plates rather than slabs because he feels that plate is a more abstract term. And floor plates are a sandwich construction which is derived from airplane and shipbuilding techniques. So the floor plates are 16 inches thick, and the 16 inches is a honeycomb of steel plates. So the vertical tubes are made of circular steel tubes, and the floor plates are made of a honeycomb of steel plates. If we look at a structural floor plan, we can see the honeycomb. And we can see that it's not regular and it's not standard. And so the honeycomb uh, in the lightest zones of this plan is on a 3 by 10 foot grid. So these are the areas where the structure is working the least hard. Then you can see that there are 3 horizontal bands where the columns, or sorry, not the columns, the tubes are located. They are not equally spaced, and the spacing and the placement varies from floor to floor, depending upon where the center of the circle is and the diameter of the circle. But broadly speaking, these 3 light gray areas then are stiffer. You can see that the honeycomb grid changes to a 3 by 3 foot grid in this zone. And then around each column, the darkest gray zone, the honeycomb grid is triangulated because this is where the shear forces are the greatest. So each floor plan has a slightly different layout of these vertical tubes, but the honeycomb grid always has these 3 zones: the 3 by 10 grid, the 3 by 3 grid, and the triangulated grid. So in this image then, you see a couple of the vertical tubes, and you see then the honeycomb floor grid. At the rear of this image, you see the 3 by 3 foot grid, and in the foreground, you see the triangulated grid. So this honeycomb then is going to have steel plate welded to the top and the bottom once it's complete. So there's no servicing in this structural zone. The servicing will occur in a raised floor and a suspended ceiling at each level. So the image on the left shows one of the smaller vertical tubes that has only verticals and horizontals. You can see its undulating shape as it moves up or down through the building. And then the right-hand part of the drawing shows the various pieces of it unfolded or unrolled. So and on the right is a construction photo showing one of the large triangulated tubes on site. So although the tubes are randomly spaced, and although their diameter changes from floor to floor and the center of the circle changes from floor to floor, when they intersect the plate, it is always in the form of a circle. And so components of the tubes are pre-assembled, prefabricated in the workshop with a W-section collar at floor level and a W-section collar at ceiling level. And they are prefabricated in half-story heights. So when they are brought to site, then they are welded up together to make a full story height, and then the 2 collars at floor and ceiling level then are married together within the thickness of the 16-inch floor plate. So there is some prefabrication here, but there is also a lot of site welding on this project. So in the section at the left, then, you can see the undulating tubes. It's an example of both the triangulated tube on the right and the Vierendeel tube on the left. The triangulated tube is providing lateral stability, and the vertical tube is just carrying vertical loads. In this section at ground level, you can see that the structure changes for the triangulated tube, and instead of being triangulated below ground in the two basements, it is a Vierendeel structure with only verticals and horizontals. And this is intentional because the Vierendeels then will buckle in the event of an earthquake, which means that they will be absorbing seismic energy and not passing it up through the building. Also, in terms of earthquake, the floor plate at ground level and the basement plates are separated from the retaining wall by a 4-inch gap all the way around the building so that the building can shake back and forth 4 inches in both directions without failing. And the connection of the vertical tubes to the foundations is shown on the right. You can see in the drawing at the top where it changes from the triangulated structure then to the Vierendeel structure, and then where it says spring, the connection of the tubes to the foundations is basically a ball and socket spring joint. So again, the steel tubes can roll back and forth in the event of an earthquake. So these measures for earthquakes proved to be tremendously important when the earthquake struck northern Japan several years after this building was completed. So if you want to see what it feels like to be in a building where the earthquake is happening, Google Sendai Mediatek earthquake, and you will see the videos that people recorded inside the building during the earthquake. So what you see in this image is that the interior finishes, like the suspended ceilings, failed, but the structure did not fail, and it held the floors intact, so the structure did not collapse, and this is very important in terms of life safety. So in these images then, you see the undulating columns shifting from floor to floor. And you can see the different floor heights. All of the services then will be delivered horizontally through a raised floor above the steel honeycomb plate and a suspended ceiling that drops down below that plate. So air and other services move up and down the vertical tubes, and then they pass either into the raised floor or the suspended ceiling. In the same way that the structural tubes are different on each floor in terms of their placement and their diameter and whether they're vertical or tilted, and the floor heights vary from floor to floor, the interior finishes vary from floor to floor. So each floor has a different lighting design, for example. There's no unifying character to the floors. No overall hierarchy. In the same way, the four facades of the building, which this very simple orthogonal box, each facade is different. There is no unifying envelope. So this is the front of the building where you enter. And the facade here is a double glass facade with about 3 feet of space between the two layers of glass. And so what you can see on the left is that it's a very flush and slick glass facade. There are no metal mullions. The glass is held by point fixings at each corner of the glazing, and the joints between the glass are caulked with clear sealant. In the right-hand image, we're between the two layers of glass in that 3-foot wide zone. And what you can see here is that projecting out from the inner layer of glass are vertical glass fins, and screwed to those the outer edge of those fins, they project about halfway across the void. Screwed to those fins are horizontal stainless steel struts. And those then provide the location for the point fixings for each corner of glass. So it really does look like a floating glass facade. We don't see any vertical structure because the vertical glass fins are almost invisible. So this double glass wall is helping to condition the building. It has louvers at the bottom and the top, and in the summer the louvers are open. Cool air enters at the bottom. It will be heated up by the sun and will rise up through the space and be exhausted at the top. And this is going to help to keep the building cool. In the winter, the louvers at the bottom and the top can be closed, and the sun will heat up the air in this space, and it will be like a nice heavy winter coat for the building to help to keep it warm. But this is only on the front facade. If we move around the building, we can see that each facade is different. The side facade on the left, in fact, has 4 different envelope options for a number of the different floors. And then the rear facade is more unified on the right, but again, it's different from the front facade. So what we're seeing on the rear facade then is vertical channel glass spaced apart. So it's like a glass screen or fence. And inside that are external walkways and external egress stairs moving down to the ground level. The change of envelope occurs right at the corner of the building. And so here we're looking directly at the side facade, and you can see then the double glass facade, just the end of it at the front corner of the building. And the envelope options vary from opaque infill panels, which you see the white are opaque infill panels. The layer below that is vertical channel glass. The layer below that is translucent glass. The 3 floors above the white panels are clear glass, which then has zones of fritting or patterning printed onto the glass. So ironically, the architects and the engineers really relied heavily on computers and software to design and to analyze this building. It has an irregular structure. We now have sophisticated software that can analyze non-repetitive structures. But the fabrication of the building was largely done by people, by human labor. It was not robotically welded, and was mostly done by human labor. And that's because Japan has a very sophisticated construction culture in which labor is highly valued, very respected. Labor is highly skilled, and it is a construction culture that still very much looks to human labor rather than trying to minimize the amount of human labor on the construction site. So, as I said, these vertical tubes were prefabricated in the factory. Sections of the horizontal honeycomb plates were prefabricated in the factory, in the workshops, and then brought to site and assembled on site. But there was a lot of welding on site. This was not a dry assembly or a kind of easy bolted together assembly. The entire building is a fully welded structure. So there was a lot of site welding, and the site felt more like a shipyard than, say, an American construction site where a steel frame is being bolted together very quickly. In this image on the right, you can see where the workers are standing, the two circular collars, one at the top of each floor level, the other at the bottom, and those provide then the base for the tubes to be welded to, and those are then married together on site, and the total thickness of those two steel collars is 16 inches. So they're totally hidden within the honeycomb floor plates, no downstem beams or any visible evidence of the collars at all. So here you can see one of the triangulated tubes and sections of the honeycomb floor plate with the beginning of the steel plate, top and bottom, being welded on. So Toyo Ito's objective was conceptually was to create a structure that provides a 21st century model of the paradigm of the Maison Domino. And so if we think about the Maison Domino on the left, we can see that its structure is static, that it is repetitive, it is predictable. If we look at the Sendai Mediatek on the right, we can see that the structure is dynamic, it is variable from floor to floor, and from tube to tube and plate to plate. And we can see that the Maison Domino is governed totally by a repetitive geometry, and that the Sendai Mediatek is governed by a variable geometry that has its origins in images of nature. And so this then produces a very different visual effect. The envelope of the building remains a curtain wall, and that is the wrapper that holds everything together. So perhaps, but the envelope, the curtain wall of Le Corbusier would have been just glass. In this case, we're getting a number of different envelope finishes binding the building together. So there's no singular system for the envelope of this building. It is variable. So you can see how he has placed himself conceptually in reference to Le Corbusier. And then if we look at the relationship, say, between Sendai Mediatek and the Sainsbury Centre, both of these buildings have structures that are made from circular steel tubes. So the raw material here, the component, is exactly the same. But you can see that the intentions of the architects have resulted in very different kinds of structures. So with the Sainsbury Centre, the columns and the beams are absolutely standard across along the total length of the building. So once we have a single structural bay in this building, we simply repeat it over and over again along the length of the building. The circular steel tubes then in the Sendai Mediatek produce a very different kind of structure. Again, it is variable, it is unpredictable, it changes from floor to floor, but the changes are not random. They are governed by these two simple rules of the changing diameter of the circle and the moving center of the circle. And so this geometric rule, this kind of hidden geometric rule, provides a subtle structural order that both makes it economic to fabricate, and then produces this very dynamic visual effect. Okay, that's it for today. Thank you very much.